The authors represent the fields of astronomy, astrophysics, soft matter physics, natural philosophy, and theology of science. This first chapter tackles the underlying dynamic geometry of eclipses from a scientific point of view. When and why do total solar eclipses occur? The cosmic clockwork that creates total solar eclipses essentially consists in Euclidean geometry enhanced with planetary motion. The motion of the orbital dynamics of Earth around the Sun and that of the Moon around Earth, yet strongly affected by the force of the Sun. The phenomenon in motion provides a syzygy, a lining up of three bodies. A second ingredient to the geometry is constituted by the need to match the periods of cycles of Earth and Moon so that all align, giving rise to the Saros cycle, known to the ancient world, and the more modern concept of the inex cycle. A practical note. It is well worth reading this chapter alongside a simple household experiment with a light bulb in a darkened room. Cast the shadow of a small sphere, such as a ping-pong ball, representing the Moon, onto a larger sphere representing the Earth by a diffuse light source representing the Sun. In preparation for the science, history, and art of total solar eclipses, this chapter follows the ancient precedent of an exercise in geometry, followed by one in arithmetic. Enshrined in Euclid's geometry, the most widely received textual legacy of the ancient Greek world, and in the medieval curriculum of the quadrivium, geometry remains the starting point for an understanding of eclipses. Medieval diagrams and their modern counterparts discussed in this chapter constitute one aspect of the way to understanding how total solar eclipses arise. The sister subject to geometry within the quadrivium, arithmetic, provides the other aspect to an understanding of eclipse astronomy, the key to when they appear. Intricate numerical patterns to the series of dates on which eclipses happen, identified in the ancient world, are now understood in terms of the orbits of Moon and Earth. The chapter concludes with a comparative overview of solar eclipses generated by the moons of the solar system's other planets. Geometries of the total solar eclipse and the shadow of the Moon. The principal geometric structure of the total eclipse is that of the shadow of the Moon cast by the Sun. The shadow takes the form of a cone whose base is the circumference of the Moon and whose point is directed directly away from the Sun. At every point within this conical volume, the Sun is completely eclipsed. Alternatively, an observer there has no direct line of sight to any point on the Sun's surface. The reason for the finite conical shape is that the Sun is larger than the Moon, so that the two limiting lines of sight just grazing the edges of both Sun and Moon converge at an angle very close to that subtended by the solar disk when observed from the Moon. The 13th century astronomical treatise, De Sphera, by Robert Grosseteste, covers the logic in the case of the shadow of the Earth, responsible for lunar eclipses when it falls upon the Moon, but the reasoning is identical. For a lunar eclipse happens because the Moon travels through the shadow of the Earth, which is always projected opposite the Sun. For since the Sun is a luminous body, and the Earth is a shadowy body, and rays are straight, and the Sun is larger than the Earth, it is necessary that the Sun projects a shadow in the shape of a cone, and that the apex of the shadow terminates directly on the point of the ecliptic opposite the Sun. So since the Sun is always beneath the ecliptic, so the apex of the shadow of the Earth is always beneath the ecliptic. The conical region of space directed from the Earth directly opposite the Sun is termed the umbra. All points in this volume have the property, by construction, that there is no direct sight line to any point on the Sun's surface. When any point on the Earth's surface passes through the umbra, a total solar eclipse is experienced there.